field have felt during all this struggle, this search of gravitational waves. And there are not many people left who can recount, I think, the events of 50 years ago. So I will give, of course, a report on the physics of these detectors and of the perspectives of the field, but with some historical touch. Of course, I will not give you many technology details, otherwise 1 hour will not be sufficient at all. So first of all, we are in February 2026. Is exactly 10 years since the announcement of the first detection, which was an extraordinary event for all the people in the gravitational wave community, of course. On 11th February, which is also the International Day of Women in Earth Science. So this is also, let's say, guided me to give some historical perspective. First of all, I think that everybody knows general relativity here. But however, just to remind you that following Einstein, gravity is not a force, but is a manifestation of space-time curvature induced by mass energy. This is the famous equation, which is here is the tensor expressing the geometry of the space-time. Here is another tensor expressing the presence of matter and energy in the field, and this is a constant G, C4, of course, well known. The most extraordinary symbol in this equation is this one. The fact that the geometry of space-time depends on the content of matter and energy in that region. This is really the news of this theory. So in another way, in a flat space-time, you put a mass following Newton. That's all. I mean, there is a force which attracts the masses, but the space remains with the structure and geometry. And before, following Einstein, of course, it's not true. It is just what happens. The geometry is deformed. There is no force, and all masses are free following the straight line in this, the geodetic line in this new space-time. Space-time tells matter how to move, matter tells space-time how to curve. This is, I think, what everybody knows. But maybe not all people knows how stiff is space-time. Let us consider space-time like a substance. Then the equivalent of the Einstein equation is the famous equation, can be thought the famous equation of a spring with a mass, with a force deforming the spring. Then, looking to these two equations, the role of the force here is the cause of the strain is the tensor of matter and energy. The geometry, which in this equation is the deformation of the displacement of the mass, is taken by G. So the role of this constant is to be the elastic constant of the spring, the elastic constant of the space-time. And it happens to that since C is large and G is small, at the end, the stiffness of the space-time is enormous. There is no comparison, with no substance, with no material. It's extremely difficult to deform space-time. This is why you need astronomical bodies to deform space-time in a not negligible way. But this also tells you another thing. Once you are able to deform space-time, there is a lot of energy in this deformation, even if it is very small. So when you will see a wave is generated, these waves was not easy to generate because the stiffness of the space-time is enormous, and energy that these waves brings is also very large. This is something which is sometimes not considered. So the Einstein equation, which are nonlinear equations, very complicated to solve, but is much simplified, as is known, by the weak field approximation, which you consider the space-time is the flat space-time with constant plus a small perturbation. Well, this small perturbation linearizes the equation, the Einstein equations, and magically, the Einstein equation becomes the D'Alembert equation for wave propagation. So this is the gravitational waves. This perturbation, it propagates in vacuum, like a wave, at the speed of light. So this is a gravitational wave. And the feature of gravitational waves, which I resume here, is that they have two transversal polarization states associated with massless spin-2 particles, which are gravitons. This is connected to the fact that there is no two signs, like in the electromagnetic waves for the source of gravitational wave. Only one sign. The mass is always attractive. And this makes a difference with respect to electromagnetic waves, of course. In particular, another consequence is that for the energy emitted by a system, the radiation emitted by a system, there is not a dipole term in the development in series, because the dipole term is zero because of the conservation law, and because of the conservation law of the total momentum of a visual system. So the first non-null term is a quadruple one, which means that the source is variation time of the quadruple moment of the source. The polarization pattern is this one, and the two are same. One is tilted 45 degrees respect to the others. It is connected to the spin 2, is connected to the fact that it's only one Steiner mass. So Einstein himself made the calculations for a practical case. At the time, he didn't think to black holes, neutron stars, catastrophic events. He thought about a laboratory source, like in the Hertz case for the electromagnetic wave. And the laboratory source, he thought to a big cylinder, I think 4 or 5 meters long, rotating at 4.5 hertz, because it was the maximum not to break the material, and calculated the energy emitted in gravitational wave by such a laboratory system. And the energy was so small, the amplitude of the wave was so small, that he concluded that in any case, one can think of A will have a practical evaluation value. This was like a tombstone for the generation and detection of gravitational waves. In practical way, if you think to some laboratory source and you think to some practical way, 1 kilohertz, 1,000 kilograms, if you want to realize today such a thing, then the amplitude of the gravitational waves, even nearby, is 10 to the minus 35. What does it mean, this 10 to the minus 35? Why it has no dimension? See, this is dimensionless. Because this is a strain. The amplitude of gravitational waves is a strain, is a relative displacement. 2 points at 1 meter distance, gravitational wave arrives there. The distance changes to 10 to the minus 34, 35 meters in that case. It's clear that it's very difficult to generate and obviously to detect. This slide shows a sort of approaching to the problem of the existence and the detection of gravitational waves, together with the various progresses in the observations and also on the elaboration of of possible catastrophic event in the universe. However, what is important to understand is that there was not only the fact that they are very small in any practical case, but even the mere existence of gravitational waves were put in doubt. And they were put in doubt mainly by Einstein himself. Einstein himself, after publishing the relativity and the paper with the prediction of gravitational waves, he really thought that probably gravitational waves are not there. That you can make a transformation of coordinates in which actually they disappear. Other thoughts that how you can detect gravitational waves if they strain the space, everything is changed by the gravitational arrival, even the meter with which you want to detect something. So it is clear that it is impossible to detect, even in principle, gravitational waves. So this is important. Einstein himself were doubting and saying at a certain point that they are not existing at all. So in 1957, there were, however, elaboration that possible cosmic sources, not laboratory sources. Okay, so stars, black holes, which no evidence at the time, but however, the fact that the universe could be more violent than we thought before was starting to present to the physicists another panorama, let's say. And there were this Chapel Hill conference in 1957 with the participation of the Bondi, the Vic, Feynman, Wissner, Pirani, Wheeler, let's say many stars in physics. And the goal of this meeting was, does gravitational wave exist? What we think? It is possible in principle to design a detector or just forget about it. And the birthday, let's say, of the efforts to detect gravitational waves is the day in which Pirani, in the proceeding of the conference, published this paper, which is two-page paper. Actually, one page is taken by question and answers, in which it demonstrates that with very simple argument that if you have 2 points and gravitational waves arrives, well, this is stretched. Well, if there is a laser here and here there is a mirror, then a laser pulse will take more time when the gravitational waves arrives. So you can measure that it took more time, since the speed of light is always the same. And when there is an elongation in the other sense, it takes less time. So this is measurable. Why not? The other type of detector, if you take 2 masses with a spring, gravitational waves arrives, put out of equilibrium the spring, but then once it's passed, the spring comes to equilibrium by vibrating. So why not? Why is it impossible to detect gravitational waves? Of course it's possible. In Chapel Hill was present this man. This was a key person in this story, because without this man, probably only nowadays, 50 years after, we could start thinking detecting gravitational waves. But he really was the person who started all that. He's a person which is worth a seminar himself, I mean, a lecture. He was a professor at the University of Maryland. He was an expert of microwaves electronics. And actually, he contributed to the discovery of the maser. There were 3 people accredited for the discovery of the maser. 2 people got the Nobel Prize. He didn't. But however, his paper was contemporary, let's say,
with the important insight for this discovery. The master is, of course, the father of the laser. So it was an experimental genius. Okay. So he was present at this conference. He heard the Einstein speech, clarifying that radiation waves were real and could increase the detector, and it was not the first time. You see his eyes. There is a flash of madness. he was kind of man with such a feature. At the age, well, he was son of some Lithuanian immigrants in the US. At the age of 5, he was infested by a bus. Bus hit him, and he lost. He didn't die, of course, but he lost the ability to speak and to write. He had to restart all again. In this hit, probably something happened. I don't know. Was a very original person. A very original person. He was military in the Navy. He participated to the liberation of Italy in Sicily personally, and coming back to US, he studied. He was an electrical engineer. And he went to George Gamow office, asking him if he has a thesis for an experimentalist, expert in microwaves. Gamow said, "Oh, no, I don't have anything." And this was before the cosmic microwave background detection. So I think that if he were paying attention to Weber, I think the microwave background was interpreted much before. So this is not to let's say never underestimate a request from students for a PhD thesis. So the comparison electromagnetic waves and gravitational waves. There are two polarization states in both cases, but it's different because the polarization in the case of gravitational waves is this one. I like this comment of Lord Kelvin respect to electromagnetic theory of light, because you see, we consider now today obvious that light propagates in this direction. Electric and magnetic field are perpendicular to the direction of propagation. This is the same gravitational waves, the effect distances. At that time, the example of the sound was so embedded in the minds that if a wave propagates in this direction, the effect is in this direction, the same direction, not transverse. In fact, he said, it seems to me, it's rather a backward step. The one thing about frequency intelligence to me, I do not think it's admissible that there should be an electric displacement perpendicular to the line of propagation. This is to say that going back in the history, you find that something which to us today is trivial, is obvious, was not at all affected. However, the effect of the gravitational waves arriving on a system of test particles, let's say circular test particles, in this one. So this is the guide to understand how to realize a detector, how to detect such a movement in space. And so the two methods are here indicated. In the case of the laser interferometer, which is the Michelson-Morley kind, you have a laser. The laser goes into a big splitter. If we divide it into two, go and two perpendicular arms. When it came back, a part of it goes into the photodetector, and if the two arms change in length, then it will change the interference between the two beams, and you can the photodetector look at where the gravitational wave arriving is detected through change of the optical length.
the optical path. The other way, I already explained, gravitational waves is just a forcing term hitting the harmonic oscillator. So this was the first detector of gravitational waves. There was not two masses in the spring, was an oscillator, continuous oscillator, a cylinder in which the first longitudinal mode was around 1 kilohertz. Those are piezoelectric ceramic glued on the surface, which has to convert the mechanical vibrations into electrical signals. So he put under vacuum two such detectors all around. Saying people were skeptical is underestimating what they say. However, he put two detectors, one in the Maryland and another in Illinois, and detected between Argonne and Maryland, detected some coincidences between these two oscillators. In practical, since the Earth rotates, these two oscillators were at a certain moment of the day perpendicular to the direction of the center of the galaxy. At that moment, puff, there were some coincidence event, which was the sign, following Weber, of the fact that there was a strong source of gravitational waves, some quadrupolar movement in the center of the galaxy, giving these events. And he published April 1969 evidence for this called gravitational wave edition. This was shocking respect to the community. Not only is possible to detect gravitational waves in principle, but this guy in the US detected gravitational waves, a totally new way to understand the universe. So this caused, I say, that many people started in the world to focus their attention on gravitational waves, how interesting, how extraordinary it could be to detect signals coming even from dark regions. This is like the sound, no? Of the propagating the space-time. You know the sound even from dark part of the world. If you enter in this room, and it's completely dark, but someone makes some noise here, you know there is someone here. You don't see him, but you hear him. And this is the same, to know the sources, to know the instruments which are playing in the universe by their vibration in the space-time. So in the world, many people in Glasgow, in Rome, in US, in Germany, in Italy, which were very important. Eduardo Amaldi and Rizzella. I worked in their group during my thesis work. I interacted a lot of them, and there was Amaldi is an important figure in the Italian European history of science, of physics. He reconstructed Italian physics after the Second World War and founded the INFN in Italy, Institut of Nuclear Physics, founded CERN in Geneva, and also ISA. So he's a very important person. Of course, he's known because I worked with Fermi on the experiment on nuclear radioactivity. This is a building, another topical figure at the time, Munich, with Weber-type bars. All these experiments gave null results. They repeated the Weber experiments without finding anything. And this was interesting also, because all those people starting this activity, they were doing something else. They stopped their activity and entered the gravitational wave field because they have seen it possible to understand the universe through gravitational waves. Once the answer was negative, Weber was discredited, but the people didn't come back to their original activity. They went on gravitational wave activity because in the meantime,
something happened. I mean, they passionated to the topic of the existence of gravitational waves. In 1974, there was this result from Taylor Haas, which you know very well, that there is a system, PSR 19 plus 15, which is losing energy and at exactly the rate predicted for the emission of gravitational waves. They lose energy, the system lose energy. It's possible to see through the pulsar signals, of course, but you calculate that the prediction of general relativity exactly follow the cumulative shift of the rheostat time predicted by general relativity for gravitational wave emission. So this was another important topic, giving confidence that the fact that gravitational waves really exist and can be detected in principle. In the meantime, of course, the theoretical knowledge, observational evidence about the cycle of the stars and the end state of the stars, which this object which deforms heavily space-time and can be credible sources of gravitational waves. So the field established, in spite of the evidence that Weber was wrong, with a clear objective. First, the detection, to verify that general relativity is true also in this prediction. Another, the main one maybe, is that you can look beyond the visible. You can understand where and what black holes do. Neutron stars, you can understand supernova, maybe understand gamma ray burst. The third reason is cosmological. Gravitational wave detached from the premonster plasma much before neutrinos, much before electromagnetic waves, so giving information in principle on the very first moment after the Big Bang, 10 to the minus 35 seconds. You have no probe from the Big Bang, no probe more pristine, more ancient. And also the information is that you have information which are complementary to the electromagnetic one. But the electromagnetic radiation from stellar systems, the results of an equivalent combination of the radiation emitted by atoms, atoms, and molecules. While gravitational radiation, the results of a coherent motion of mass. And in addition, you know, electromagnetic wave interacts strongly with matter, is absorbed, while gravitational radiation propagates freely, and so can bring in information into the innermost region of a star even. So can reveal features that are unique. And following the possible waveforms, you can have the information about the source. It was the waveform Lovell, because it was very, very clean, the signal of two compact objects peering together from binary orbit, and from the shape of the wave can realize the masses, the distance, the spin, many information, even if the wave is quite short. When I do talk for general public, I invite people not to be skeptical of the fact that the 1 second waveform gives you a lot of information. For instance, if you are in a dark room and someone play a note in the piano for 1 second, you know that there is a piano. You know which note has, well, if you are a musician, you know which taste, come si dice, quale tasto, which note has been played, and if you are one of the people recording the pianos, you know even if the piano is a good quality or not. In 1 second waveform, your ear understand all that. So a modern computer from this waveform coming from neutron stars or black holes knows if they are neutron stars, if they are black holes, the distance, the spin, and the inclination of the orbit. Well, here there are the noise, but this is trivial. This is just for the general public. You can hear noises because they are in the audio frequency for these sources. For instance, for a compact binary, this is for a neutron stars, or for a black hole system, or this is the chirp. You can hear the chirp if you connect the waveform to a loudspeaker. For supernova is a burst, or this is the ksh, is the white noise. For this is the violin note. Is exactly one frequency. So we have to attribute importance to Joe Weber, even if he was wrong. Archibald Wheeler, what his mentor said, he was the first. After our work together in Leiden, he embraced gravitational waves with religious fervor and pushed them for the rest of his professional career. Sometimes I wonder if I instilled in Weber too much enthusiasm for such a monumental and difficult task. Whether he ends up being the first declaration waves, or whether someone else does, or some other group, matter little. In fact, he will have the credit for paving the way. No one else had the courage to look for gravitational waves until Weber showed that he was within the real possibility. Actually, the wife of Joe Weber, I knew Joe Weber, I will show now a picture in a moment, told me that all was the beginning, was due to the fact that their son, few months of life, very young, had the habit to hit his head against the wall of the cup of the bed. So Joe started making long nights awake to be careful for this fact. And so, since he had to be awake, he decided to study generally. And he passionate towards the possibility of an experiment to detect some of the prediction, in particular gravitational waves. This is something which is very funny. And also very romantic. So this was pictures of the evolution of Weber bars, the cryogenic bars, the second generation. They cooled to low temperature to reduce thermal noise as much as possible, employing superconducting technique to convert the vibration from mechanical to electrical using superconducting quantum interferometric devices. So putting all at the limit of the technology, having at the end, this was cooled, for instance, the refrigerator at 10 millikelvin, which was a record for such a large mass. Results, many upper limits, but no detection, no evidence. This is the Explorer at CERN. This is Allegro, is the name of this. It was in Louisiana, Baton Rouge. This was in Australia, the Firestack. This is David Blair. He was also in Italy, in another laboratory of NFN, in Legnano, the Massimo Cettori and Stefano Vitale. I think you know these people. Stefano was the eye for the LISA Pathfinder. So these are the 5 detectors which created an array for making coincidence altogether. Results, nothing. I mean, upper limits, but no, nothing else. This is what the spherical detector was very nice because started in the Netherlands and also in Brazil. Because spherical detector is the natural evolution of the cylinder. It is omnidirectional. It has 5 quadrupolar modes following the spherical harmonics of order 2, so it can detect not only the wave, but also the direction of the wave, and also the polarization. So it was fantastic. But I mean, since in the meantime, the interferometers started showing that the design sensitivity can be reached. and the interferometers are much better. There are not concentrated bandwidths in a few hertz. They are large bandwidth from 20 to kilohertz. And they are scalable. I mean, starting from a tabletop of 1 meter, they can go to 1 kilometer. And this means sensitivity. You cannot gain sensitivity of factor 1000 easily with the bar detectors, while with interferometers was much natural go to these distances. So after many years of struggle and of work, all the people working with bars, they joined the colleagues already started with interferometers, bringing a lot of know-how. Because you see, every experiment in gravitation, the basic is to suspend a mass isolated from all the other source of noise and monitor the movement of this mass. This is true from Cavendish time. This is true for the bars. Of course, you have to see the vibration of an isolated system, but it's also true for the interferometers, in which you have suspended mirror. It's not the laser detector. The laser is the meter, but the real detector will interact with the gravitational waves is the two suspended mirrors changing their distance. And the laser is the most practical way to measure this change in distance. To remind the role of the Italian groups and Edoardo Amaldi, I proposed in '94 a conference on gravitational waves. There was not a conference on gravitational waves at the time. People of our community reported the results in the Texas Symposium, General Relativity, Marcel Grossman, but there was not a conference, international conference on gravitational waves. Started in 1994, and then now every 2 years is in a different continent, different countries. It was important in 1997 when Barry Parish created the Gravitational Wave International Committee, and this committee decided that the cornerstone conference is this one. I like to show this. Is the first Edoardo Amaldi conference, Gravitational Waves, in 1994. I was the organizer here, but there are a lot of people here in this picture. All the people of the community. This is Adalberto Giazzotto, and this is Alain Brignier, the two leaders of Virgo, who founded Virgo. This is Stefano Tale, again. And so you can show the whole people. This is Ron River, and there are many people. This is Alberto Lobo. I like to show the picture here in this room. So, why was it difficult? You take 1 meter, you divide 10,000 times, you have the thickness of a human hair. If you divide the human hair thickness for 1 million times, you have an atomic diameter. If you divide 100,000 times, you have a nuclear diameter. Still, you have to divide the 1,000 times the nuclear diameter to have the goal that was considered as the minimum, the minimum for gravitational detector. This is why it was not easy. It looks impossible to measure displacement of 1/100000th of a billionth of a meter. And this was possible with this instrument. The instrument is a laser beam. To show you the animation. I mean, maybe this is trivial, but just to people which is not familiar, this is the laser in the schematic layout. The laser goes with a certain wavelength in the two opposite directions. There is the end mirror, 3 or 4 kilometer distance per vacuum. When they compose together, and then apart goes the detector. If you arrange the things in the way that the interference is negative, you have here a black spot. But if something happens and there is a relative movement between the two ones, then you have light. Its lights appear, disappear at the frequency of the gravitational waves, and the intensity of the spot gives you the amplitude of the gravitational waves. So this instrument was able to reach this sensitivity. Of course, there's a small amount of noise. The noise are the Brownian motion, the thermal motion of the mirrors and the wires. There is scattered light noises. There is Newtonian noise due to the local movement of the object coupling gravitationally to the mirrors. This is radiation pressure from the beam, the laser noise in frequency and in amplitude, at the photodetector with shock noise. So it's very difficult, however, and the sensitivity, which was indicated here, and the strain and the amplitude increase of the gravitational waves, this gives you the idea of the range of frequency. This is important also to show that there are other detectors, even future like LISA, which are in a completely different frequency range. This is one of the main reasons that both detectors should be pushed. In practice, then, there are a lot of many other experimental tricks. First of all, the light in this house goes back and forth many times. So in practice, it's like if the detector were more wrong. And there is a part of the signal to put again inside to increase the sensitivity. So, I mean, it's quite complicated. Of course, there are 3 detectors of this class, 2 in the US, and 1 in Italy. The noise influences the sensitivity in this way. The seismic isolation goes to improve the low frequency part. It's possible to have a low frequency sensitivity if you do not isolate very well against the local seismoacoustic noise. Here, in the central part, the nominal noise is the fluctuations in the thermal fluctuation in the mirror and also in the coating of the mirrors. And here, to reduce this is the shock noise. So you need to have high power laser. There are no devices on the market that you can buy. Everything have to be developed, especially uniquely for reaching sensitivity of the detector. This also explains why it was difficult. It takes so long. So all the technology were pushed to the limit. And finally, in September 14, 2015, the 2 detectors in the LIGO Hanford and Washington detected the same waveform. Why LIGO not Virgo? Because LIGO was approved 2 years before. It started taking data 2 years before Virgo. So the first detection was the one of LIGO. But the community was built together, LIGO-Virgo Collaboration, because both collaborated not only to the various experimental part, but also to the data analysis, to the modeling. So it was in practice one single large group accredited. And so you see, this is a noise detector, right? But at a certain point, the noise takes the shape, which is the one typical of gravitational waves. So the clean end waveform is this one, indicating the spiral phase, the merging and the ring down of 2 masses, one 36 solar masses, the other 29 solar masses. The final mass was calculated to be 62 solar masses. The 3 solar masses missing were emitted as gravitational waves. A conversion energy following E equal mc squared of 3 solar masses. Never before human beings have seen this conversion of mass to energy. It was an incredible amount. In an atomic bomb are a few milligrams converted in electromagnetic radiation. Here was 3 solar masses. The speed of these 2 black holes at the moment of the merging were about half of the speed of light. Half of the speed of light for masses of solar masses. So
this is what the reconstruction of the event. The lighter part is the crest of the wave. The wave originated 1,300,000,000 light years distance. So was originated when on the Earth were the first form of very elementary life. Arrived on September 14. Also, the Earth have felt not so much. Of course, this is exaggerated. Otherwise, earthquakes I can't imagine. So this time there were this detector. So glory, glory, hallelujah! As you know, the 3 Nobel Prizes for the fathers of LIGO, and these are the picture of the 3 detector with also CACRA, who has the current detectors in the world. So after the first detection, we have seen many others, mainly from black holes mergers. However, a few years later, 2017, there was this fantastic event in which there were not black holes, but no light was detected at the time of all our binary black holes mergers, signals, gravitational waves. But this time, this time was prepared when there was agreement with many other telescopes, and an alert signal from the gravitational detectors were sent to the telescopes around the world in cases of a possibility to point in the sky to see what happened. And that day, actually, something happened. This is Marika reporting these results, because this is a frequency amplitude plot, and this is the history. It was a gamma ray burst detected by Fermi, and just before this, there was the detection of a signal from LIGO, from the LIGO and Virgo. So the detectors realized that there were a region in the sky, origin of these waves, a region in which possibly something was occurring. And all the telescopes, these are not a model, these are images. All the telescopes were pointing in that region of the sky to see if something was happening. And you see this point, this is where they have seen online, live, that something happened. During the next hours, these things had different colors, and this was the binary neutron stars merging and massaging, let's say, during the signal. This was the brightness versus the wavelength in the following days, and you see this defines lines corresponding to the nucleus of heavy elements, the K of nucleus of heavy elements. And in fact, it was understood that all these elements marked with yellow color are formed by merging neutron stars. So when you have a conference in public, you can say, if you have something of gold, you know that this gold comes from some merging neutron stars occurring in this region of the universe. It was calculated the amount of gold, just to impressionate people, the politicians, the amount of gold generated by this event was about 100 times the mass of the Earth. Amount of gold. Some difficult to go there to take it, of course. So this model, this was the reconstruction of what happened. So it was, in this case, 2 neutron stars. There was a flash of gamma ray burst of gamma rays, and then this was the part of history monitored by all the telescopes So, making a long story short, all these blue dots corresponds to merging of black holes. On this representation of the signals detected so far. This orange corresponds to the detected neutron stars. This yellow are the neutron stars already known. And these red are the black holes of binary system already known. But apart this yellow and red, all the rest is due to the gravitational wave detectors of this the present generation. Find out more in this system. So at the end, it was incredible to pass from the exist or not. Difficult to see, we don't see nothing, to the fact that every week we have a system and we monitor different kind of masses, different kind of system, also very interesting and very strange systems. So which contribution comes from nearby here, from IFI, is here. The contribution, of course, is commissioning, calibration, the responsibility of some subsystem, the development of instrumental baffles. The baffles are essential to monitor the stray light of the laser and to give a feedback to the position of the mirrors and of the rest of the system. So it's quite important. So the monumental success of the detector is here indicated. First detection at the start of the multi-messenger astronomy, and then demonstrate the polarization probability, the mention of the gravitational propagation speed, because the gamma ray bursts and the gravitational waves arrived 1 second one from the other. Probably the second is due to the mechanics of the sources. However, on such a distance, this means that the mass of the photon and the mass of the graviton are the same, 1 part on 10 to the 15. So this was an upper limit which was not existing before. And then it is a test of gravitational observability, of course, but really of the system, all the waves seems to be good polarization states. These are alternative measurements of the Hubble constant, because since it is, you mark the distance. Once you know the masses, the waveform tell you the masses, the amplitude tell you the distance. And once you know the distance by this gravitational wave measurement, you can compare this distance with the one of the redshift of this galaxy at the source. So we have direct, let's say, determination of the Hubble constant, totally different. So the resource in 2017 solved the understanding problem of the origin of the first sound shock first. The fact that the neutron star merge are assigned for the formation of some experiment. The fact that the black hole binary system merged in the edge of the universe. This is now obvious, but it was not obvious before the detection. And then we discovered the population of stellar mass black holes much heavier. It was detected. I said the speed of gravitational wave equals the speed of light, and all the rest. Now, this is the present future. We investigate gravitational waves in all the frequency region. We have hints on the climatic gravitational wave through the polarization beam modes of the cosmic background, which is not yet certainly detected, but however, this is a way. We can get with the pulsar timing array, which I know you know what it is a series of radio frequency detectors monitoring the pulses of the various pulsars. And if the gravitational waves arrives long wavelength, then you are these pulses are modulated, so you can understand the supermassive black hole coalescence over isotopic gravitational background from some source. Liza, I'm there to say something. Liza, here, this is the another possible detector. I mean, to use the moon as a spherical detector, putting the seismometers on the moon and waiting that the normal modes are being excited. This is the frequency range that we from the one of the ground-based parameters, which are more for the high frequency sources, of course. So in the rest of my talk, I will just say something about the Einstein Telescope. I started with Einstein prediction. Let us arrive at the Einstein Telescope, which will be in the shape that I will say in a moment. Will be a fantastic infrastructure to be realized. We don't know yet where, but we know next year where and which is the shape. We will go underground while the US, they will stay on the surface because they can go to length like 40 kilometers or 20 kilometers. Apparently in Europe is difficult or impossible to have such a flat space in which you can avoid to this big excavation. So this is the sensitivity jump from the present detector to a factor 10 in amplitude sensitivity means a factor 10 in the distance of the sources that you can detect. Factor 10 in distance means a factor 1000 volume, which means a factor 1000 rate of event. So see, if at the moment we have a few events per week, then we have thousands of events per week. Incredible with what you can do with this experiment. And I wanted just to mention why it is important to go, why we consider to be important to go underground is to be able to have sensitivity at very low frequency. The fact that there are seismic waves, and so it's possible to shield a Newtonian signal. You can only reduce it by going underground. Sensitivity at low frequency means being able to detect the chirp in the earlier stage. Means more time to alert also the telescope saying when there will be the merger. So this is why it's important to have sensitivity at low frequency. Also to detect some pulsars which are in that range of frequency of pulse. So the combinations of distances and mass explorer, the number of detection which we expect, and detection in very high signals provide a width of data with the EP that have the potential to trigger evolutions in astrophysics, cosmology, fundamental physics. I just mentioned some highlights here because I want to give you the important, but and all the information is in this monumental article by Michele Maggiore as main author. Michele will just for. This is the archive where you can find everything you wanted to know about the physics, the astrophysics that you can do with the Einstein Telescope. So having given to this information, I can even stop here, but just to remind you what this means is to do fantastic things. Just one thing I want to mention. I want to mention that we will be able to detect black hole merging even at a distance before stars formation. This means that if we detect chirp signals coming from that distance, they have to be primordial black holes. They have to be black holes formed by fluctuation of pure energy when even not the matter was present in the image. This is just one of the lines I wanted to give you. And then also that know the rational state of stars being able to see all the tidal effects in the network. So much physics. Just you must know we are studying and that's the roadmap, the places. ICE has an important role because Mario is the project director, Mario Martinez, and he was the chair until 2 months ago of the collaboration board. The collaboration is spread around the world, and there are 3 possible sites for putting the triangle or an L. Sardinia and this region has already support of local government. They committed to put €1 billion if the detector is done in their country. The cost of one triangle is around €3 billion. So, however, all the other countries should contribute. And this is important. We are trying to decide if do 1 triangle or 2L in 2 sides. The 2L has advantages in the determination of the direction of the source and the polarization of the source. So it is better, but of course you have to realize 2 sides and not 1. Thank you for your attention.
Questions? Yes.
I have one historical question. Has anybody found the force of the signal detected by Weber at the beginning? Was it ever explained
Neutrino?
by Weber in the beginning? That's basically the signal.
No, well, Weber was so such a fantasy that he also proposed a neutrino detector form of a crystal, but no one taken seriously what he did. However, by all know, I mean, apart there is new physics, let's say, but for what we know, all these detectors, gravitational waves, cannot detect neutrinos. They can, of course, correlate with neutrino detectors in case of a supernova in the galaxy. Then it will be very interesting to see the correlations between gravitational waves and neutrino coming from a supernova. But apart these, let's say, inventions of Weber, there are no way to detect acoustically or by lasers.
Other question.
So is there still room, now that we know much more about gravitational waves and starting from the fact that they exist, is there still room for solid state bar detectors? I'm guessing they're kind of cheaper than €3 billion.
Yeah, I mean, thank you. Because of course this is my youth. No, what we imagined actually with Alberto Lobo and with Michele Maggiore, we imagined that the ideal for kind of detector was a xylophone of spherical detector, various sides. Holosphere was even better, in such a way to cover a large frequency span and to detect gravitational wave this way. The cost of that could be less than 1 large interferometers. But however, this means having various groups wanting to push this research. The community is not so large. So we are concentrating now on the ET, 1 side, 2 sides, L, triangle. This is the debate at the moment. Underground. I have to say that myself with Michele Maggiore once again, we try to imagine, but why we have to go underground? Okay, this is the low frequency noise, the seismic noise. But if we do like the Americans, very long. It's true that you cannot realize something like 20 kilometers in Europe. So we were investigating the map with Mario Martinez, looking for places in Europe where there was no large anthropic activity, let's say, and flat territory. And we found that in Spain, near Zamora, there is a place which was very good for that. And we went there with Mario, and we spoken with the local president of the Caja Rural de Zamora. We need money to have money to have at least a feasibility study. No, because you don't understand. Like, it's flat. You go there and you see everything's flat. But of course, there are lands, there are bridges, there are highway, no, but there are villages, there are farms. So you need to study the seismic noise in the place and to make a study, a single study with money for that. The community of gravitational waves in Spain is not so strong. And also our tentative were quite timid because not to disturb the rest of the collaboration, which is deciding on certain kind of detector. But I have to say that my American colleagues, and Barry Barish comes here once per year for our scientific committee council, which is the chair. He says, we never considered the possibility to go such deep underground because it's so natural to be on ground. Also, it's expensive. And however, in Europe, we decided to do that, which, however, is very good for low frequency noise. This is what to say. And so we are pushing now this. It's called, well, the resonance detectors is alpha. Well, there is a resonance detector in the map. This is lunar detector. This is the revenge of us to see that this is not the sphere here, but the sphere there, very large, fantastic. This is our detector. But I mean, this is easy. Could be easier because there are many missions on the moon. This is now the fashion. So you have to put interferometers. There is interest on some industrial interest on that. This can be done. What is unknown is the kind of results that we will have.
I question about future generation. Suppose that when we issue the sensitivity, suppose increases in sensitivity of locality. Yes. So about the increasing sensitivity of third generation. I suppose maybe wrong that increasing sensitivity at low frequencies, 1 to 10 hertz, that can come at the expense of increasing the sensitivity around that.
That's a very good question because I didn't put the detail, but actually the detector is not only one detector. When we say one detector is two, one specialized to low frequency and another to high frequency. So there must be different in several kinds, including the power of the laser and all that kind. So there are a system of two lasers coexisting. So just to optimize exactly what you say.
Yeah, thanks for the talk. I know that Diego Blas is proposing a mission on a reflector and a ball there. And what do you think of it? Do you think it's going to be an interesting approach?
For many aspects. Technological aspect, first of all, and also to fly with the imagination. Certainly, we don't have figure out which kind of sources are that frequency. Yeah, it's an unknown that came out. I'm quite skeptical about the frequency range sources. I mean, we don't know astrophysical sources of that kind, or exotic. Have to do with information, topological defects, something which for a technician, something which is exciting maybe, for experimentalist is always a little bit more. But however,
I think it's referring to the low frequency emission, not to the high frequency.
okay. Yeah, well, sorry, because he's proposing to.
Yes, so it's, there's one that made it through the crack.
No,
actually.
the one
In between Lisa
Yes.
and TPA.
measuring the orbital changing,
Yeah.
say, the change of the shape. This is very hard to detect. It's really a practical challenge. It says that it can complete. But also there, in my experience, it passes a matter of some. It seems to be very complicated already to have measured something you are under control in the laboratory. Something there, however, should be done. I think that must be done. Because I think that's we don't know.
Other questions? Maybe I have a question about, so you said very quickly, as you presented many things, that that now we know with the detection of gravitational waves, of course, that the velocity of gravitational waves is the velocity of light. So how well we know this, and which are the consequences of
To be more correct, the velocity of gravitational waves is the same of light, one part of this is what we have upper limits also for the mass of the photon. So the upper limit of the mass of the graviton stays the same order of magnitude one of the photons. And mainly we know, since it's coherent, the waveform right here is very coherent. There is no dispersion. Actually, that our mind mass is near to zero, at least at the mass of the photons.
and how interesting you think it would be to actually push this limit farther. Is it?
You can have many exotic theories which predict that the planet will have a mass, the photons will have a mass. So, but at the moment, let's say that the Einstein general relativity predicting the two polarization states which I showed is really strongly, the confidence is much stronger than before.
Thank you. One last question? No? So if not, let's thank Eugenio, right? Maybe online we have questions. Any question online? Check the chat. Just be sure. Anybody?
No questions. Thanks for the talk.
No.
Questions?
No.
Okay.
Okay. Thank you. Thank you very much.